Imagine you can have drones or aircrafts that can navigate and fly without the need for the GPS signal, or even a spacecraft that can fly between planets and moons without the need for a feedback signal from Earth. This also can be the case for cars and any vehicle on Earth that can move without the need for the GPS signal or satellite feedback. To know how they work, stay tuned and watch the video till the end. The question starts from what if we could measure time, gravity, magnetic fields, and even motion with extreme precision using the strange rules of quantum physics and the language of quantum mechanics? And this is exactly what the quantum sensing is about. This might sound futuristic, but now quantum sensors are being used and being integrated slowly in many applications. And in this episode, we are gonna have an overview and a quick glance about the applications of quantum sensors, the different types of them, and the challenges of using them at the moment. So try to watch the video till the end to know all of these details. What we have now from the capabilities, we can use classical sensors to measure the change in physical quantities like in temperature, in electric signal, but also in magnetic and electric fields and gravitational fields. Typically, the precision of these sensors would depend on the way that these sensors or this apparatus can detect the change in these physical quantities. The current sensors now, they are called the classical sensors and they have their own limitations in measuring the changes. But what if you can use quantum systems like atomic systems or ions and use this tiny quantum systems in measurement on a very fundamental level? This what is quantum sensing is about the use of quantum systems to measure physical quantities with very high precision. And this can be involved to measure time, like using atomic clocks, and also the change in magnetic field, electric field, gravity, and also acceleration and rotation as well, and even temperature. And this is very important for sensing direction and also navigation. And without the need for digital signal, you can use like an analog signal from the quantum sensor that's already exist on your vehicle or exist in your device. Even these applications can be extended to disease detection, like, for example, detecting dementia and the formation of certain proteins that cause some diseases in real time and identifying the causes of these diseases in real time, which will help in making the medicine much faster and much more efficient. But the question now, what makes the quantum system or this quantum thing when it's used in sensing a very reliable sensor? So the language of quantum mechanics has many applications. With the language of quantum mechanics, we can make communications with them, we can communicate, we can do computing with them, like what we see in quantum computing, and also we can use sensors or sense with it. And the idea is that the quantum systems can leverage the superpositions, the interference, and the behavior of, for example, the entanglement. And if you can use these patterns, you can use atomic energy levels or any quantized system to make measurements. A simple way to think about this is that if you have a normal sensor, which is like a good ruler, the quantum sensor is this ruler, but built in with very extreme, precise behavior of atoms and particles that can even give you extreme capabilities of measurements. But how does the quantum sensor work? On a high level, the quantum sensor follows a certain workflow. First, you need a quantum system that has some sort of energy levels or some levels that are quantized or are separable. So they should be orthogonal or extremely separable from one another, like a ground state and excited state. It is very important to have this because this is would allow you to create the superposition and also quantify the change that happens between these two level systems. So, in a nutshell, you need to create something similar to a qubit, two level quantum system, like a 0 and 1, in order to be able to measure the changes that might happen. The second thing, you need to prepare this quantum system in a controlled state. So, you need to have a quantum state which you can control to extreme precision. This could be an atom or an electron spin or an ion or a photon or even a superconducting circuit, which also can emulate the behavior of atomic system. Once you have this quantization of levels, so you can have a 2 energy level or a 3 energy level, but now for simplicity, let's assume you have 2 energy level and those are separable and they are exist in a quantum state which is in your control. So you have extreme control on this quantum state. Now you can put this system in a superposition. It means that you can have a combination or a linear combination between the ground state and the excited state. So between the 0 and the 1 if we adapt the model of the qubit system. So the system can exist partly in 0 and partly in 1. Now, once this system is exposed to an external quantity, like have an interaction with a certain physical quantity or a certain environmental quantity, then there is some detuning would happen. So the controlled state or the state that you have already defined would change a bit. So you need now to measure this, and typically the measurement of this will be done via an external device. We call it driver Hamiltonian, and this driver Hamiltonian will just help identifying the changes that happen. So now here is the thing. You need your quantum system to be extremely precise. So the quantum system will detect the change via the changes that or the slight change that would happen in the quantum state. And now your role will be to compare the original quantum state and the new quantum state. So once the system evolves and it adapts a new quantum state, you have your own new quantum state and the old quantum state. You can use what we call autocorrelation function, which means that you need to know the overlap between the original wave function or the state function that describes the system in the default state and the state function which describes the system after the change that happened. So you have two situations now. You have the original quantum state and then you have the new quantum state which has been altered due to the interaction with the physical quantity that you would like to measure. By comparing those and evaluate what we call the autocorrelation function, you can see the overlap between them, how much overlap happened and how much change that happened. And this would give you an idea about the change that happened in this physical quantity. If you can quantify this, like you can quantify the change between the two vectors, the state function, the vector of the original state function and the vector of the new state function, then you sort of have created a way to measure this physical quantity. How this measurement happen for the new quantum state, you can use, for example, lasers, you can use microwave pulses or even electronics to measure the new quantum state. And then you compare it on a computer, the new one and the old one, and compute the autocorrelation function. And once you quantify that change, that will give you what happened to this quantity. You can see this, for example, for laser interferometer. If you have a certain frequency of light between all of the interferometers in space, and once the gravitational wave started to ripple in the fabric of space-time, because the gravity is sort of intertwined in the space-time, then by comparing the new situation and the old situation, you can detect or correlate this to the change that happened in the fabric of space-time, which will give you a clue about the gravitational waves. Similarly, for time, you can put atomic clock on Earth and you can put another one in a spacecraft and then compare the two states. And this will give you an idea about the time dilation, the change that happen in time due to the relativistic effect because of the spacecraft that already moves at a high speed away from Earth and also away from the gravitational field of Earth. So now in one sentence, quantum sensing works by preparing a dedicated quantum state, and this is a very delicate quantum state which letting the environment leave a tiny footprint on it. And then by reading that footprint in a very precise way, we can do this. And we can see this in the following workflow on the screen again. Now, why quantum sensors are extremely precise? Because you are using the fundamental nature of the universe. You are using fundamental quantum systems that you exist around you. Like, for example, the atomic energy levels. These are the most fundamental levels which you can measure the changes between. Or, for example, if you go to an elementary particle and you have a spin, like spin of electron, then you have two distinguished states like spin up and spin down. And these are a fundamental thing in nature, which presumably you cannot go beyond it anymore. So you are using the fundamental properties of nature and use these properties to your benefit to create a quantum sensor which can detect the changes in that. So that's what makes these quantum sensors are very sensitive. And in that sense, it can be used to sense a gravitational field if you can map the gravitational field and the gravitational fluctuations on Earth and also the magnetic field of Earth. You can use a combination of two or three quantum sensors. You are sort of creating a very effective localized GPS system in the vehicle that you are using. So you might not need a GPS signal coming from space because those quantum sensors, with the proper use of AI models and the machine learning, they can combine the inputs, the different inputs from these quantum sensors, and then create sort of an effective 3D mapping and 3D navigation for the vehicle. For example, it could be an aircraft, it could be a car, a bus, a ship, anything without the need for a GPS signal or relying all the time on the GPS signal because maybe the GPS signal will be used also as well. Secondly, you can use it in medicine. You can trace the formation of certain proteins or production of certain cells in real time. So you can know how this is happening in real time by having these extreme measurements. Major part of the advancement that happened in civilization is the way that we were able to measure precisely things like we to measure the projectile of things but also the trajectory of motion and even map the motion of satellites very effectively and also extreme the blood pressure having very accurate simulations of the planetary system so we can place telescopes in space in a very good positions. So part of the huge advancements that happen in science come from the advancements that happen in meteorology, and the quantum sensing provides very extreme meteorological instruments that can provide very phenomenal and powerful capabilities in measurements. Also, you can use them in magnetic and many other things, even in fabricating materials and also injecting medicine in the body. You can also use quantum sensors, for example, in cryptography and in cybersecurity. We have put forward in Molkit, which I'm a co-founder of. Molkit is a startup based in Paris, and we have put forward early on a conceptual use case for using ultra-cold gas quantum sensor in optical fibers to detect the tampering that happen in optical fibers, but also to detect any errors or any deformations that might happen due to any natural cause like earthquakes, but also the vibrations in earth that might damage the optical fiber. So it can be used for detection, the hacking detection, and also the tampering, the natural tampering that might happen from nature and help in securing and maintaining the optical fibers and maintaining the connection in real time. So with that, we are using the phenomenal capabilities of quantum sensors. Other applications could be in quantum sensors used to increase the mileage of cars. So Toyota, in collaboration with some other universities in Japan, they have developed a diamond-based quantum sensor which can detect the electric signal and electric currents from the electric batteries in real time and help in the charging capacity, which led to increasing the mileage of about 10%. So quantum sensors can even add an extra lifetime for EVs and electric vehicles and help maintaining the electric batteries to live longer. Now, what is the main challenge for quantum sensors? So the obvious challenge is that the quantum sensors are very bulky. They are huge and they cannot be easily installed in vehicles or in aircrafts like airplanes or even in small drones for agriculture or any other applications in defense system or anything. Because such systems, they are very bulky, they need very huge cooling mechanisms that can cool them and then make them shielded from the noise that might happen from the environment. So if you have a self-driving drones for surveillance, for military applications, or you have it for agriculture, or for example desert maintaining, so you can know which parts of the desert you can, for example, rehabilitate and use it in farming, or in for example in a human body or anything, you need to have the quantum sensor intact and shielded from the unwanted interactions. And typically, that might require some cooling and some shielding for the quantum sensor. So that makes the quantum sensor very bulky. You can also see that the gravitational sensors also are very bulky as well. So they are not sometimes easily integrated in devices. So depending on the application and the precision that you would like to achieve, you might increase the cooling and the electronic ecosystem around your quantum sensor. So that's an obvious challenge. However, with the developments that happen in science and the advancements that happens every day, quantum sensors are getting smaller and smaller. So with enough investments and enough use cases and enough studies, quantum sensors will get better, especially they can help in farming and also detecting diseases in real time, which this would require very small quantum sensors, not like an aircraft where you can put a huge one. So these ones would require a smaller size. If you like to explore some use case about the quantum sensors and see how quantum sensors can help your application, feel free to contact us and we can help you in Molkit crafting a use case or giving you training about how quantum sensors do work and how you can benefit from them. Until we meet again, see you and be well. If you have questions, please drop them in the comments below or contact me on the email taha@tahasalim.com.